Thank you, Sebastian. Thank you very much for the invitation. It's a pleasure to be here today. Okay, so we've heard about photonics, now onto solids. I will introduce the ENVI Center today in the context of quantum computation. I will go into more depth with regards to the question how can we eliminate errors on a physical level, and how can we eliminate errors on the level of the computation using quantum error correction. And this is work that I did as a researcher at the University of Konstanz in the group of Guido Burkhardt. Nowadays, I'm a researcher in, is this pointing? Yes. Today I'm a researcher, I'm working for Quantinuum. So if you're interested in ion trap software, I can encourage you to come to my presentation tomorrow at 11 a.m. In the workshop room 2. All right. So what makes a quantum register a useful quantum register? For this, the community has agreed on certain criteria, the Defects criteria. So we have these several platform candidates that are leading the field at the moment. They are very different quantum systems with different properties, so we had to sort of agree on certain criteria. The first is that our system needs to be scalable, so it's not enough if we have 1 or 2 qubits. We need to be able to scale up and to build large computers with, in the end, millions of qubits from it. The next point is that we need to be able to reliably initialize our system. We need long coherence times, which means that the quantum information that is stored on the system needs to be able to sit there for a while and long enough for a significant quantum calculation to take place. We need a set of gates, a so-called universal set of gates, that can be transpiled to be able to calculate any arbitrary quantum algorithm. And of course, we also need to be able to look at the system, to measure, to find our result. Okay, so all these platform candidates, we've just heard it from Jens, that they are noisy intermediate scale quantum devices at the moment, and we are trying to build something that has a significant quantum advantage where we can show that the quantum computers really outperform the supercomputers. And we want to do a fault-tolerant, we want to go to the fault-tolerant regime. And in the fault-tolerant regime, we can, the remaining error on the calculation, we can deal with it on the level of the codes and the algorithms such that we suppress it, and we can, in the end, do an error-free calculation on the systems. But there are challenges that affect all these hardware candidates, and that I want to go into more detail about today, about using on the example of the ENVI Center. We have limited gate fidelities, so we have errors that occur during our control operations. We have a limited set of native gates. Our systems have a limited connectivity among the qubits. We have a loss of information, and scalability is in all cases a problem. Okay, so let's look at the case of the ENVI Center and how we tackle these challenges in the case of this specific hardware platform. So the ENVI Center is a solid-state-based system. It sits in a diamond lattice of carbon-12 atoms, and it's a single defect. So one carbon atom has been replaced by a nitrogen atom, and its nearest neighbor site is vacant. And then we get a central spin of the system, the electron spin, and we use this central electron spin as the first qubit, so the qubit levels are encoded into the spin, so it's a spintronic system. And by the native hyperfine interaction of the system, this spin couples to the spin of the surrounding carbon-13 isotopes in the material that are there within 1.1% abundance, natural abundance. And we get the connectivity of a central spin system. So this is, for instance, very different from the 2D grids that you get when you look, for instance, at superconducting hardware. So the central electron spin here mediates all interactions. And the interaction between the carbon isotopes is too weak to make use of it in this case. Okay, so scalability can either be achieved by coupling more carbon-13 isotopes to the central spin, and in terms of seeing them and characterizing them, I think the record is at more than 70 coupled carbon spins. And the other way to scale up is by proximal NV centers, where you couple the central electron spin to the other central electron spin, either by means of dipolar interaction, where they have to be very, very close to each other, or by photonic or even phononic interaction. The basis gates are rotations on the Bloch sphere, so it's a very kind of it's a very good gate set that you get, because you can rotate all the single qubits, either as single qubit gates freely on the Bloch sphere, or you can also do conditional logic with rotations. So you get coupled between like 2 qubit gates, between 2 coupled qubits. And what is also very advantageous in this system is that the nuclear spin qubits are very well protected in the diamond lattice, and they have very long coherence times. And they are so well protected that we can even operate the system at room temperature. So we do not have to use the cryogenic regime. Yeah, the system is optically addressable for initialization and readout. And with that, we have fulfilled our DiVincenzo criteria, and I would like to look at the electron-nuclear entangling gate. How does this work? So we look at the Hamiltonian. So this is the Hamiltonian of the entire system here. I'm happy to go into detail later if you want me to, but I do not have the time to do that now. Just saying that we use a 50 nitrogen atom and do some approximations, and then we can end up with this rather simple kind of 4-level energy scheme here. So every bar here indicates a different energy of the system. Here you have the electron spin levels, and these here are the nuclear spin levels of the nitrogen atom. And you can see that when we look at this transition here, and when we drive this transition, so when we operate, we target the electron spin, and we flip it from 0 to -1, conditioned on the state that the nuclear spin is in the -1 state. And we have exactly this energy difference here, and with a microwave pulse, we can address exactly this energy transition and perform conditional logic on the system. So this is then in terms of linear algebra what we can express, and we can express this in this approximation exactly if we choose the appropriate driving strength and gate time. Okay, so far so good. Now we have a system that fulfills our criteria, but we have errors. And okay, so errors on a quantum computer occur due to several reasons. One is that our control operations are faulty. The other is that the interaction with the environment occurs unwanted. So we have desired interaction with the environment, but we can't control that fully. And we have unwanted interaction with the environment, where we lose the quantum information stored on the qubit. Then we also have that our qubits interact with each other. And we have, of course, also wanted control to qubit interaction that we need to engineer. And we can have, essentially, we deal with these errors with 2 strategies. The one is that we reduce the errors and the unwanted interaction on the physical level as far as possible. And the other one is that we deal with the remaining errors by quantum error correction and quantum error mitigation, where we've just heard a full talk about by Jens Eisert. So I want to go into more detail for the case of the NV center now. And we again look at our entangling gate that I've just shown you, but now we look at the errors that occur. And so this is the Hamiltonian in the joint basis of the 2 qubit levels. And this off-resonant Rabi frequency here indicates essentially, when we look at the system here, And you see, we want to drive this transition, but we also, by doing so, we will always also hit, we have a finite probability of hitting the other transitions, of inducing unwanted spin flips on the system. And that will decohere the quality of our gate. And essentially, this is given by how strong we drive the system. So this is kind of the gate fidelity, the gate quality that is plotted here over the strength of the driving field that we use to induce this spin flip here. This is the formula we plot. And we compare the real system against the wanted interaction here. And you can see that only in a very weak driving regime, we have a good gate quality. So 1 is the best quality. And by going up, like with the driving strength, this quality decoheres significantly up to a pure randomness here. But the problem is, so what current schemes use is they do a very weak driving and then combine that with complex pulse sequences to stabilize the qubit and to keep it from losing information into the environment, because it sits there for quite a while if we have a weak driving pulse, and the operation time is very long, and we lose information. And then you avoid this regime where you induce this error. And we came up with an idea where we incorporate the off-resonant drive in our gate scheme by making use of synchronization effects. And this way we can show that we can do high fidelity fast, very fast compared to the weak driving regime C0 gates. And the essential idea is that we look at these points where the system oscillates. I can't go into detail about this now, but we look at the points where in certain points of the driving strength it reaches a full fidelity, and we come up with analytical expression for that and show that you can then completely suppress the error that you induce. Yeah, we can also show that this holds when you have more complex systems. And yeah, so there are analytical as well as numerical ways to suppress this error. And it gets very quickly very involved when you look at a 14 nitrogen atom that has 3 levels to spin, and when you couple the carbon isotopes. And we also show this for the case of, yeah, when you go back to the system. So you can also drive the carbon spin here, conditioned on the state of the electron spin, and this is a slightly different scheme, and we can also incorporate this resonant, this synchronization effect and show a good gate quality here. Okay, so in the remaining minutes, I would like to give you an intuition about using quantum error correction on these systems. So this is a very simple quantum error correction code. It's the bit flip code and the phase flip code. It's a very, yeah, it's in principle, it's like, as long as it's not concatenated, it can also be just a classical repetition code, and it's a simple example where you can investigate the properties of quantum systems for error correction. So we have a state, and we copy, I mean, we don't copy it, of course, because you can't do that in quantum mechanics, but we create redundancy by entangling it with 2 other code qubits. And we assume that noise occurs on the system, and then you entangle it with more auxiliary qubits, the ancillas, and you can measure them, and then you can look at your system and find out the type of error that has occurred here by looking at the measurement results, and you do not destroy your encoded information. So that's the basic idea. But, so this one works on paper, but if you want to implement this on a central spin connectivity, you have to swap your qubits around because you just don't have the connectivity that is required. And you can see that it becomes very ugly and involved. And we compared it in this publication here with superconducting hardware. I can't go into detail about this now, but just saying that the error rate that we achieve in the end, the logical error rate when we encode, is a lot higher than the one we achieved with the superconducting hardware. But a nice feature of these systems is that we can make use of the central spin connectivity by so we can make use of the fact that the electron spin at the same time sees all the coupled carbon spins, and you can make use of this for a more kind of complex quantum gate, a multi-qubit controlled rotation. And we use this here, and then we are able to very cleanly encode this quantum, this repetition code by using these gate identities. And this is a connectivity that is not provided for instance, with superconducting hardware. And then you can see that when we compare it with the same code with superconducting hardware, that the NV center performs much better for all different sets of parameters that we check. Yeah, I think this is the end of my talk. I showed you that, we use synchronization effect for high fidelity gates on NV centers, and that we can show them for different kind of gate schemes, and can also extend the parameter range of B1. I didn't show that, but we can. And these are the publications that I mentioned, and I thank you very much for your attention.